The Dbscan algorithm was developed by Esther, Kriegel, Sander, and Xu in their 1996 KDD paper cited at the top. Dbscan stands for Density-Based Spatial Clustering of Applications with Noise. One of its key strengths is that it discovers clusters of arbitrary shape. Its basic intuition is to cluster observations in high-density regions and mark observations that lie in low-density regions as outliers. A first key concept is the epsilon neighborhood, which consists of all points within a radius of epsilon from the point P defined as shown. A second key parameter is min-PTS, which represents the minimum number of points in the given neighborhood NP. Here you can see this illustrated. The epsilon neighborhood of point P is 4, whereas the epsilon neighborhood of point Q is 2. If min-PTS equals 4, then the density of P is considered high, whereas the density of Q is considered low. Dbscan differentiates between 3 types of points. A point is a core point if the density around it is high. Hence, a core point is located at the interior of a cluster. A border point is a point with low density but located in the neighborhood of a core point. And finally, an outlier is not a core or border point. You can see this illustrated below in case min-PTS equals 5. A point Q is directly density reachable from a point P if P is a core point and Q is in P's epsilon neighborhood. Note that P is not directly density reachable from Q, and the measure is asymmetric. A point P is density reachable from a point Q if there is a chain of points P1, P2 until Pn with P1 equals Q, Pn equals P, such that Pi plus 1 is directly density reachable from Pi. You can see this illustrated if min-PTS equals 5. You can see that P1 is directly density reachable from Q. P2 is directly density reachable from P1. P is directly density reachable from P2. Hence, there is a chain from Q to P. Finally, 2 points P and Q are density connected if they are commonly density reachable from a point O. You can see this illustrated in the figure at the bottom. Note that density connectivity is a symmetric measure. We now have the necessary background to start introducing the Dbscan clustering technique. Assume we have a dataset D and 2 parameters, epsilon and min-PTS. A cluster C is a subset of D satisfying 2 conditions. The maximality condition states for all PQ if P belongs to C, and if Q is density reachable from P, then also Q belongs to C. The connectivity condition states for all P and Q belonging to C, P and Q are density connected. Note that a cluster contains both core points as well as border points. The Dbscan algorithm then works as follows. Randomly select a point P from the dataset D. Then retrieve all points density reachable from P in terms of epsilon and min-PTS. If P is a core point, a cluster is formed. If P is a border point, no points are density reachable from P, and Dbscan selects the next point of the dataset D. Continue until all points have been processed. At the end of the algorithm, the points not belonging to any cluster are considered as noise. Here you can see some of the key characteristics of Dbscan listed. First, it can handle clusters of different shapes and size. It can find non-linearly separable clusters, as you can see illustrated in the dataset at the bottom. Note that this dataset cannot be nicely clustered using k-means clustering. When using Dbscan, there is also no need to fix the number of clusters up front, which differentiates it from k-means clustering. However, one of the key drawbacks of Dbscan is that it cannot handle varying densities.